All right, in this lesson, we are going to talk about both kind of sequences, but we're introducing a new one called geometric sequence. So for our warm-up, it says determine the pattern in each sequence, then find the next three terms. So looking at number one, I always like to see if it's adding a common difference. And so here we are adding 6, and then from 9 to 15, we are adding 6. From 15 to 21, we are also adding 6. Okay, and so if we continue the pattern, that would take us to 27. 27 plus 6 is 33. 33 plus 6 would give us 39. And so because we are adding, this is called an arithmetic sequence. Arithmetic always goes with adding, and the way I remember that is they both start with A. And so anytime you see adding, think arithmetic. Okay, in this next sequence, our pattern, we're adding 2 and then we're adding 6, so clearly not arithmetic. And so from here, I try multiplication. So 1 times 3 is 3, 3 times 3 is 9, 9 times 3 is 27, 27 times 3 is 81, 81 times 3 again would be 243. And because I don't have my calculator, I'm just going to leave it at that. And this is actually a different kind of sequence called geometric that we will talk about later throughout this lesson. All right, in this next one, we're going from 200 to 100, which is subtracting 100, but then we're only subtracting 50. So once again, this is not arithmetic. But the pattern I'm noticing, it's getting divided by 2 each time, which is the same thing as multiplying by 1/2. And so if we were to continue the pattern, we would get 12.5 and so on for the next 3 terms. Just keep cutting in half. Okay, and so this is also what is called geometric. Geometric goes with multiplying, and arithmetic goes with adding. Okay, and so when we're talking about a recursive form, for arithmetic, we get to any term by taking the previous term and then just adding whatever that common difference is. Okay, that number we are adding each time is called a common difference, denoted by D. And the only operations you can use are adding and subtracting is just adding a negative. And so technically we could just say adding here. And then for the explicit form, which is a little more useful if you need like the 100th term, is you just start with the first term and you add that common difference n minus 1 more times, because you're starting at A1. You just need, if you were trying to get to say the 10th term, you would just be adding D 9 more times to get to that 10th spot. Okay, so for geometric sequence, this is a bit different because we're multiplying. And so our common difference is now called a common ratio. Ratio is for multiplication. And then the operations we're allowed to use is multiplying. I'm not even going to write dividing because dividing is multiplying by a fraction, and we always want to view what we're multiplying by. Okay, and so for our recursive, you get to any term, and this common ratio is denoted by R. You get to any term by taking the previous term and multiplying it by R. So we typically write that in front of the previous term. And then for the explicit formula that we can use to say find the 100th term, we would start with the first term and we would multiply it by R n minus 1 more times. So notice the n minus 1 is an exponent. Repeated multiplication. If I were to say try to get to the 9th term, I would be multiplying by R 9 times. And so repeated multiplication, say I had like 4 of them, we would just write it as R to the 4th. And so now we have an exponential expression, whereas when we have repeated addition, that turns into multiplication. So if I had plus D, plus D, plus D, plus D, that's really just 4 times D that I'm adding. Okay, and so that's why you're seeing n minus 1 being multiplied in arithmetic. That's why you're seeing n minus 1 as the exponent for geometric. All right, so in each of these examples, we are going to write the explicit and recursive form of each sequence, then find the indicated term, if possible. And so first we have to just identify what type of sequence it is. And so looking at number 1, we're going from 5 to 15, then 15 to 45. So that is multiplying by 3. Okay, and so this is geometric. Geometric goes with multiplying. And so that means we have a common ratio. And that common ratio is 3. And so when I write the recursive notation, that means I get to any term by multiplying 3 by the previous term. That's what that notation means. For the explicit form, we get to any term by taking the first term. And so our first term here is 5. And we multiply it by the 3 n minus 1 times. So to find the 8th term, we would take that 5 and multiply it by 3 7 times. That's why the 7 is my exponent. Okay, and so we can use our calculator to do that. So 5 times 3 raised to the 7th is 10,935 for our 8th term. Okay, this next one, we're going from 1,000 to 500, from 500 to 250, from 250 to 125. That is multiplying by 1/2. So once again, this is geometric because we are multiplying and we have a common ratio. And that common ratio is 1/2. And so for recursive notation, we get to any term by multiplying 1/2 by our previous term. In explicit notation, we take the first term, which in this case is 100 or 1,000, and we're going to multiply that by 1/2 n minus 1 more times. Okay, so taking that 1,000 and multiplying it by 1/2 5 more times would give me my 6th term. Okay, so to find the 8th, our exponent was 7. To find our 6th, our exponent is 5, always one less. Okay, and so once again, we can use our calculator for this. 1,000 multiplied by 1/2 to the 5th. So 31.25. Okay, in this next example, we're going from 12 to 17, 17 to 22, 22 to 27. And so this time we are adding 5 each time. So because we are adding, this is arithmetic. Adding goes with arithmetic. They both start with A. And so we're calling this a common difference. Okay, and our common difference here is 5. And so in recursive notation, we get to any term by taking the previous term and adding 5. Okay, and so notice for recursive, we are multiplying. Notice for arithmetic, we are adding. For the explicit notation, starting with the first term, which in this case is 12, we are going to add 5 to it n minus 1 more times, not an exponent. A lot of people start putting that in the exponent. This is repeated addition, which means multiplication. And so to find the 15th term, I would take 12 and I would add 5 to it 14 more times. Okay, you always do it one less than the term number you're trying to get to because you're starting at the first. If you add 15 more times, you've gone to the 16th spot. Okay, and so while we have our calculator, we can go ahead and just type that in. 12 plus 5 times 14 is 82. Okay, looking at number 4, we are going from 2 to -2, from -2 to 2, from 2 to -2, -2 to 2. So we are multiplying by -1. Anytime you see it going from positive to negative, positive to negative, positive to negative, that means you're multiplying by a negative, because the negative keeps getting canceled out every other term. And so our common ratio is -1. So in recursive notation, we get to any term by taking our previous term and multiplying it by -1. They usually don't put that multiplication dot, but I like to write it. But if you don't see it written, it still means multiplication. They may not even write the 1. They may just put a negative. All right, so for explicit notation, we take our first term, which in this case is 2, and we multiply it by -1, n minus 1 more times. Okay, and so for the 9th term, we take the 2 and multiply it by -1 8 times. Always 1 less than the term number, so you don't go too far. And so in our calculator, we know -1 raised to an even power is going to be positive, so this is going to be 2, but just to prove it to you, -1 in parentheses raised to the 8th power is going to be positive. Anytime you raise a negative to an even exponent, it's going to be positive because you have enough to cancel out. Okay, and so this next one, we're going from 14 to 9, 9 to 4, 4 to -1. So we are subtracting 5 each time. So because we are subtracting, this is arithmetic. We are adding -5. Arithmetic, common difference, -5. And so in recursive notation, we get to any term by taking the previous term and subtracting 5. In explicit, we get to any term by taking our first term, which in this case is 14. And we are going to subtract 5, n minus 1 more times. Again, no exponents. This is adding, not exponential. This is adding, so it should be linear. Okay, so to get to the 25th term, we would take 14 and subtract 5, 24 more times. And we could do that without a calculator, but while we've got it, 14 minus 5 times 24 is -106. Okay, this next one's going from 10 to 5, 5 to 2, and then 2 to 1. So first of all, I'm going to see if it's subtracting 5, but then it's subtracting 3. So not arithmetic. And then it looks like we are multiplying by 1/2 to get from 10 to 5, but then that's times 2/5. So not geometric. Okay, and so neither. All right, in these next set of examples, it says, given either explicit or recursive form for the following geometric sequences, write the other form given the following. Okay, so we're given that the recursive form is any term with the previous term times 3. Okay, and so if our first term is 5, we would be multiplying by 3 each time. So just kind of listing out the sequence. We would go from 5 to 15 to 45. And so in explicit form, we start with our first term, which is given to us, and we would multiply it by 3, our common ratio, which we see from the recursive form, and then n minus 1 more times. Okay, here we're given the explicit form. So I can see my first term is 10, and my common ratio is 8. And so all we need for recursive form is the common ratio. We are multiplying 8 by the previous term. Okay, you can either put that 8 in front or after. I more than often see it in front than after, like it's written here. Okay, here we're given the recursive form. We are multiplying by 2/3. That's our common ratio. And then our first term is 15. And so for our explicit form, we start with the 15 and we multiply it by 2/3 and minus 1 more times. All we need is the first term and the common ratio. All right, given the first term and the common ratio, find the indicated term. So they're telling me my first term is 4 and my common ratio is 2. And so my explicit form would say take the 4 and multiply it by 2 n minus 1 as our exponent. So for our fifth term, we would take the 4 and we would multiply it by 2 4 times. Okay, and so in our calculator, 4 times 2 raised to the 4th is 64. Okay, and so the 4 is your first term, the 2 is your common ratio, and then the 4 in the exponent is because we are looking for the fifth term. Right, here our first term is 100 and our common ratio is 1/2. So my explicit form would start with the 100 and it would multiply it by 1/2 n minus 1 times. So for the third term, we would take 100, multiply it by 1/2 twice. Okay, we know 1/2 squared is just 1/4. 1/4 of 100 is 25, but of course you can type it in if you have a calculator. Okay, for this next one, my first term is -2 and my common ratio is -5. So I'm starting with -2 and we are multiplying it by -5 n minus 1 more times. So for the 8th term, which is what they're asking for, we would take the -2 and multiply it by -5 7 times, always one less. Okay, and so in your calculator, -2 times -5 raised to the 7th power is 156,250. Okay, and so now for this last example, we have a chemist is studying the growth of a bacteria strain. The number of bacteria in a petri dish is 550 and it doubles every hour. Okay, does this scenario represent arithmetic or geometric? How do you know? And so this is geometric because if it is doubling, we are multiplying by 2. That's what doubling means, multiplying by 2. And so we would say geometric because we are multiplying. Geometric goes with multiplying. Write the sequence in recursive form. So in recursive form, we get to any term by taking the previous term and multiplying it by 2. Write the sequence in explicit form. Well, we're starting with 550. So we take that 550 and we multiply it by 2 and minus 1 more times. Okay, so how many bacteria will there be after each number of indicated hours? And so here we're starting at 0. So after 0 hours, we still have 550. And then after 2 hours, this is actually an exponential situation. So we just keep multiplying it by 2 every hour. So time to get to 2 hours, we would have 550 times that 2 times. So our exponent would be 2. and would get 2,200. Okay, and so here, after 4 hours, we have multiplied it by 2 4 times. To get 8,800. And to get to 10 hours, we would have 550 being multiplied by 2 10 times. Which is 563,200. And then after 20 hours, we have multiplied this by 2 20 times. Which is 576,716,800 bacteria.